Welcome, fellow chemists, to a video inspired by Numberphile's Legend of Question 6, which is about an incredibly difficult problem posed at the 1988 International Mathematics Olympiad. Like mathematics, there is an International Chemistry Olympiad too. Qualification to represent the United States is sponsored by the American Chemical Society and begins with the local exam in which thousands of students participate nationwide. From there, about 1,000 or more top scorers are nominated for the national exam. Then the top 20 scoring students attend a 2-week study camp, from which the 4 Olympians are finally chosen. Today's question is from part 1 of the 2019 national exam, where students were presented 60 multiple choice problems to complete in 90 minutes. Let's meet question 58. The question is remarkably short, and the molecule is not overly complex. So how many participants answered this correctly? If it was 100%, I wouldn't be making this video. 50% is a reasonable guess, but no. 25% even more so if all of them guessed each option roughly equally, but it was 14%. Surely the question isn't that difficult, right? To answer it, I will ditch the picture, but everything else is the same. The answer choices go in order with the hydrogens on the top, so option A is red, B is orange, C is yellow, and D is green. It is a short question, but the examiners have hidden the simplicity behind it with technical jargon. So in situations like this, if we can simplify it, we should. Although the words are ridiculous to an unexperienced chemist, bond dissociation enthalpy is simply the energy required to break a bond. The question specifies which bond has the smallest dissociation enthalpy, and so will break with the least amount of effort. The less energy required, the weaker the bond is. So a bit of translation allows us to rephrase this question as, which bond is the weakest? Now that we have a simpler question to answer, let's take a closer look at the options. The first of 2 properties we can easily identify and use to answer the question is the classification of the carbon as primary, secondary, or tertiary. I've mentioned this in prior videos, and the card will bring you to one of them. Option A is bonded to 2 other carbons, so that makes it secondary. The same is true for option B. However, option C bonds to 3 other carbons and is tertiary. Option D only bonds to 1 other carbon and is primary. Next up is hybridization, which I mentioned in a couple of instrumental analysis videos. While the options are sp, sp2, or sp3, you can think about it as the number of atoms the central carbon bonds to thanks to this nice coincidence. If we write out all the exponents, we see the number of atoms each carbon bonds to is simply the sum of the superscripts in the hybridization. In option A, carbon makes 4 bonds but to only 3 different atoms. This makes it sp2. When carbon bonds to 4 separate atoms, which is what happens in B, C, and D, its hybridization is considered sp3. This is very useful information because there is a nice trend between hybridization of carbon atoms and the strength of carbon-hydrogen bonds. The greater the S character, or alternatively the lower the P character, the stronger the bond. Since the carbon in option A is sp2, it is the strongest of the 4 options. Since we are looking for the weakest, we can rule it out. Hybridization helped us eliminate one answer choice, so let's dig deeper into the classification. The way we do that is by asking what would happen if the bond broke. Well, we would get a radical. Something I've covered before on this channel is the stability of radicals, so of course you've watched those videos and know this already, but I'll be nice and remind you that methyl radicals are ridiculously unstable, but the stability increases through primary, secondary, and tertiary. Something else to know about the stability of radicals is, the more stable they are, the easier they are to form. And if they are easier to form, then the bond that was broken must have been weaker. According to our classifications, option D is primary, and so if that bond broke, there would be a primary radical. This cannot be the answer because the original bond must be pretty strong if the radical is unstable. So you've certainly deduced that option C is the weakest bond because the resulting radical is tertiary. To that I say you definitely applied what is on the screen now, but are those all the possible radicals? To answer that, we need to look at the molecule again. For clarity, I need to make one adjustment, and that's to move this hydrogen down. Now, the only way to be sure the answer is C is to analyze what happens if we break the bond in option B. This is undoubtedly secondary, which we would assume is not as stable as the tertiary, but there is something special about this radical, and that is its proximity to the double bond. In this special case, the electrons in the double bond and the lone electron can actually move around to form a new structure. Notice nothing has changed except the locations of the radical and the double bond. This can revert back to the original structure, and back to the new one, and back to the old one, which is known as resonance. We have not seen this behavior from the previous 4 radicals, so say hello to the 5th, the allylic. Resonance increases the stability of this radical, which makes it even more stable than tertiary. This means the bond that broke to form it must be even weaker. Therefore, we can identify the answer to the toughest question on Part 1 of the 2019 U.S. National Chemistry exam as B. This particular question reminded me that there is one type of radical reaction involving alkenes that I did not yet make a video of. Since it involves allylic radicals and spoiler, a 6th type known as benzylic, it makes a perfect follow-up to this one. Until that one comes out though, thank you very much for watching. Feel free to send me absurd questions from your own exams and perhaps I can make a video out of them.